Hello there. In this video, I'm going to teach you how to write functions in YASM x86-64 assembly inside of Ubuntu, although probably any YASM assembler will be fine. I've covered these topics before in other videos, but I thought it would be nice to put them all here in one single video to make it a little bit easier to understand. Okay, so first off, what the heck am I talking about? Well, when you have a program, let's say we have a higher level language program, and we have void, or actually probably not void main. Let's say int main, and we'll forget about the arguments. And inside of main, it just sort of calls f, and then we have an f function over here, and it does stuff, right? So that's the basic idea of having a function that you can call, and calling it. We sort of take the whole process for granted in higher level languages, but in assembly, we have to do a lot more from scratch. So I'm going to show you about how to pass arguments, how to pass integer arguments, pointer arguments, floating point arguments, return types, double, like floating return types, integer return types, pointer return types, how to use special registers to actually pass the arguments into the functions, how to write a function in the first place in assembly. So that's basically what we're going to do. Before I get any further here, I just want to point out that this video is not about the basics of assembly, nor is it about the basics of Makefiles or some of the other related technologies that I'm going to show. I've covered everything in this video in a previous video. So if you find yourself getting lost and you don't understand what I'm saying or what I'm doing, you probably want to look at my previous videos, because this is sort of a summary video to kind of help you really lock down on the concepts of writing functions. Okay, so for starters, this right here that you're looking at is a Makefile. This is not a Makefile video. If you want to learn how to make Makefiles or why they're awesome, see my other videos. But I'm just going to assume at this point you're either willing to research my other video, or you already know, or you don't care how to make a Makefile. So, we're just going to skip this. I'm going to close it. The next thing I'm going to do is write a driver function, or sorry, a driver module. And what I'm going to do is I'm going to write this program that I'm showing you now as a hybrid program, a program with modules of different languages. So this module right here is going to be C++, and then we're going to have an assembly module, and then they're going to be able to call each other. So the first thing that I'm going to do is I'm going to name some functions that are going to be inside of my assembly module, and also name some functions that are going to, well, name a function that's going to be just inside of the C++ module, but it should be callable by the assembly module. So for that, we use a little block called extern C. And long story short, that disables name mangling, which C++ does in order to provide overloading functionality. So we're basically going to disable overload functionality in order to have simple function names. That way, assembly can call these functions. And also, when we attempt to call a function inside of assembly, we'll just call it by its simple name rather than try to mangle the name based on the arguments and return type and such. So that's something we have to do for compatibility, at least for this video. And I'm just going to move on. So basically, you just take the keyword extern and you put a C in a quote, and then you make a block, right? A little braces scope, and then you just list prototypes of either the functions inside of the current module which you would like to demangle, or other modules functions that you would like to be able to call in a demangled, or I guess a non-mangled way. Mangled meaning name mangling. Okay, so then I'm going to copy paste the main function that I'm going to do. So this is a hybrid program, which means, there are several different modules of different languages. And usually what I like to do is have a module called the driver, which just launches the program, and it contains like the entry point. Like, see how there's like the main entry point, which if you know how to do it other languages, this is usually where you start in C++ or like the GCC libraries. So this is the entry point for our whole program, and then once we're inside of here, we're just going to print out a message to the user. We're going to make a C string, and then we're going to call on the assembly function. We're going to give it, some numbers, some integers, and some floats, and we're going to give it our C string. And then when we're inside of the assembly function, we're just going to print those things to prove that we know how to call and we know how to receive data from C or C++ into assembly. And then we're just going to print, goodbye, basically. Okay, so I'm going to make another, another function in the driver. so that assembly has something to call. Because I don't just want to be able to call assembly from C, I also want to be able to call C from assembly. So I'm going to put in something that we can call on from assembly here. I'm going to call it my CPP function, and it's just going to have like some arguments, just some nonsense arguments. And all it's going to do is just print out that it's entering, print out the arguments, and then just sort of say goodbye and then just return a value to the caller. We're going to return a floating point value to the caller. And we're going to return a floating point value to the caller. Okay, so notice how at the top here I have in the extern C, my CPP function. It's the same thing that we see at the top is now at the bottom. And that just means this normally would be compiled and linked with name mangling. And so because it's in the extern C block, there's no name mangling. And the reason that works with an extern C block is because there's no name mangling in C. That's sort of like a C++ thing with overloads and like all these extra data types and whatever. Okay, so we have like the basics for our driver. It's a simple module. The hard work is going to be inside of assembly. So maybe before we write assembly, no, you know what, let's write the skeleton of the assembly, and then I'll start explaining what it means to call back and forth and to make functions and things like that. Okay, so for starters, I'm just going to make a data section with a bunch of stuff inside of it, and I'll explain it just very briefly. Again, this video is not about the basics of assembly in YASM. If you want to learn the basics, go see my other videos, but for now, I'll just assume that you understand why we're making variables in the data section and kind of how to do it. So you can see here, I'm making a bunch of null-terminated strings. They're null because they have a 0 at the end. And I'm just saying, well, here's a message when we begin the program. Here's a message to announce we're about to print some integers, to print a C string, to print some floats. Here's another message for this, another message for that. It's just a bunch of messages, right? Then a CRLF, that's just, taking the cursor down to the next line and then back to the very beginning. So it's like basically a new line. And then I'm going to have some floating point numbers. And I'm going to have an A and a B number. And then I'm going to have a B and a D that I'll send somewhere else. And so I'm going to populate them with numbers from the start. The B and the D that just are not being sent, they start at 0 because we're going to receive those numbers from C. And then we're going to get a return value as a floating point from the C function that we call. So we're just going to store it there. So I'm just like making a bunch of room to store some variables. And then here we're just going to do system write, and we're going to send to standard output. That's covered in other videos. But basically, we're just going to be printing stuff. Okay, so section text. Now this is where the program actually starts. Well, sort of. This is where the program contains instructions to execute. So section text, and the first thing I'm going to do is I'm going to name some external symbols that I have for myself just to help me print integers and floats. So, if you've seen my other videos, you know that you can do a wide variety of things to sort of print characters and numbers if you were clever. And you can also call on C library functions like printf if you really wanted to print floating point numbers inside integers and stuff. So you don't have access to this library, so don't worry about putting this part in your code if you're working at this from home, unless you're someone that has taken a class that I've taught somewhere. For now, just assume that this just lets me print very easily. No problem. You don't really need that if you're just kind of experimenting with the functions. Okay, so then extern my CPP function. This is the name of the function that we made in the driver. My CPP function. Notice how it's over here. My CPP function. We're just letting our assembly module know that there's a function in another module that we should be able to call on. Even though all of these modules are going to be linked into the same program, we still have to do this just to let the assembly module know. Okay, so now we need to make a function called myAssembly function. If you look at the top right here, we had this other D name mangled prototype, myAssembly function. So we have to actually write that somewhere. It's not in the driver. Let's write it inside of assembly. So myAssembly function is going to start right here. Boom, right there. So this is when we kind of start on the basics of writing a function. So for starters, hopefully you understand labels. If you don't understand labels by now, you might want to see my other videos. But basically, a label is just some sort of an alphanumeric symbol that you just kind of write. It's sort of like a variable name. You can't use every symbol available. I would just start with using letters and numbers and the underscore. Of course, you can always experiment if you want to see what's allowed and what's not. Just type something and see if it compiles. So the label starts with just, this name and then a colon, right? So that's a label. You can jump into labels. Like if we were somewhere else in the program right now, we could, like if we wanted to do an infinite loop, we could say jump and then the name of the label. And what would happen is execution would go back up to this label and then it would jump again, it would go back up. It would be an infinite loop. But we wouldn't technically be calling a function. We're just sort of jumping. So labels are sort of the first step, but we have to do a little bit more to actually make a function. So we have an assembly function, which right now is just a label. And in order to make it callable from the outside, we have to mark it as global. So remember when we marked my CPP function as extern, that means we can call a function that lives somewhere else. Now we're marking this function as global, which means it lives here, but we want other modules to be able to call on our function or our label. Okay, so how do we actually make a function? Let's see, the first thing that you should do is try to understand that all functions return, even if they don't return any values. So I'm going to do a return statement. Under the hood, what this is actually going to do is crash the program if you just jumped into this label and didn't call it like a function, because the return instruction will look onto the call stack and try to find a return address for wherever this function was called from, and then go do a jump instruction to return there. And so if you just jumped into this label and then there's a return, it's going to pop something off the stack that's not actually a return address and probably crash the program. So that means now that we have a return statement, we definitely have to call this like a function. And I guess that's pretty easy because, well, if we were inside of assembly and we wanted to call another function, let me just show you real fast. I'll say some other function. If we were inside of this label, for some reason, we could call the above function by just saying call and then the label. So now it's being treated like a function. What the call instruction really does is it just looks at the address of the next instruction that would have been executed. So, whatever, let's say we have like a nope on the next line, whatever the memory location or the relative memory location is of that nope instruction, it's going to push that onto the call stack, and then it's going to just do a jump instruction to this label. So then later when we hit this return statement, then it's going to look onto the call stack and it's going to find that return address, which is going to correspond with the nope instruction. And the return instruction is going to do a jump back to that address. So basically you have to use the call instruction to get there and then use the return instruction to return from there. And then now we can actually call it a function. But then there's other things that functions have to do to behave themselves without crashing the program. So for example, notice up here that I've copy pasted the, let's see, call on assembly. Oh, I think I forgot to update that. Let's see, call on us. Yeah, it's supposed to be called my assembly function now. Hold on. Let me update my, my solution. Whoops. Hold on. Call on. There we go. My assembly. Okay. So I've got my solution up above on another monitor. So I have the prototype of the function here. It's just going to return nothing, and it's going to like take in a long and a double and a long and a double and a character pointer. So some mixed arguments. And then my intention here is to save these arguments with some registers. So notice how I'm saying we're going to use R12, 13, and 14 to save the arguments A, C, and E. And we'll talk about why we're not saving the other ones with those registers in a second. But basically, we're going to use those registers. So the thing about the registers is we have to do something called respecting the ABI. Respect the ABI. The ABI stands for the Application Binary Interface, and it's just sort of like a standard that governs all of the things that you can do and you're supposed to do when you're working with x86-64 assembly. So the ABI is pretty cool. Hang on a second. The ABI is pretty cool because it actually standardizes things. For instance, if we didn't have the ABI and we didn't respect it, then we couldn't actually call on assembly from C++, or vice versa, because C++, the higher level languages, they're going to use the ABI. So if you try to do things your own way, then all you're going to end up doing is wasting time and energy coming up with two different ways of doing things when you could have just done it the ABI way, right? So, and one of those ways, your way, wouldn't even work for cross, module calling. It would only work internally to your own program. So we're going to respect the ABI. So what does the ABI say about these registers? And again, I've talked about this extensively in other videos, but let me pull up a fun book that I love to talk about. So this book right here, I did not write it. The book here is written by a really wonderful professor, Dr. Ed Jorgensen, PhD, and this book is totally free. I'm not selling you anything. This is literally, you can just go to this professor's website and download his book for free. And he's already given me permission to just tell everybody, to just share it with everybody. If you look in the license area, it's a copyleft license. So it's sort of like the spirit of open source, just sort of like sharing knowledge and stuff. So it's awesome. So I suggest everybody, follow the link that I hopefully put in the video, and grab a copy of this book. But basically what I'm going to do is I'm going to go to a special area and I'm going to search for callee saved in my little PDF here. And so that would be, I guess, section 12.8.2, and it's called register usage, subsection 12.8.2. Notice how it lists all of the registers and kind of how they are typically used. This falls under the scope of the ABI, so this is not all the ABI is, but this is one of the things you're supposed to do when you're respecting the ABI, is you're supposed to sort of like respect the way these registers are supposed to be used. Notice R12, which is one of the registers that we're going to use, is designated as callee saved. So that means whoever is being called has to preserve that register if they intend to mess it up. So for example, if I just had this function here, move some value into, R12, I have now basically broken the program. If any, a C function or other library that you didn't write, just anywhere else calls on this function, then their version of R12 is going to get destroyed by what I just did. And so I'm not respecting the ABI. When this function returns to the caller, they're going to expect that their original data was intact. And if it's not, the program's not going to work. It's going to screw up. So respecting the AI means you have to preserve any register marked as callee saved, or that's one of the things that it means. So notice how R12 through R15 are callee saved. So we have to respect the ABI now and sort of preserve 12, 13, and 14. We can do that pretty easily with some push and pop statements. So I'm going to do push R12, push R13, push R14. And now what happens is those values are actually on the stack now, and I can retrieve them later at the end of the function. Even if I destroy them while I'm inside of the function, I'll just restore them right before I return. So we usually call this the prologue, because it happens before the function does anything. And then we have to make sure that we pop those values, because you have to be careful with the stack. If you just start pushing values and you don't restore the stack to its original state by the time you return, you've basically broken the program. It's either going to crash right away, or whoever called it is not going to function correctly anymore. So let's do some pops. We're going to do 3 pops, and we'll call this the epilogue, which means something we do right before we exit the function. And keep in mind that the order of the pops should be reverse of the order of the pushes. Notice how we're popping in reverse order from what I did before. So we're going to pop 14, 13, and 12, whereas we pushed 12, 13, and 14 before. If you pop in the wrong order, like if you try to do it in the same order as the pushes, then you're still going to end up destroying data for the caller, because you're going to be restoring data to the wrong registers. So just keep that in mind. Okay, so now the ABI is being respected. Let me see, by the way, do we have enough to actually even run the driver right now? We're just calling it, and then it didn't really do anything. Yeah, I think we could probably, this might compile. Okay, let me just check this out. I'm going to say clear and make run. Yeah, it compiles. Okay, so the driver printed its hello message. If you looked at the driver again, it's just sort of saying like hello from the driver. And then when the driver comes back, it says the driver regained control, and nothing really happened because, well, we didn't do anything in our assembly function yet. But at least we're calling multiple modules. And again, if you want to know how to do hybrid programs and linking and compiling and all that stuff, see my other videos. For now, I'm just going to move on. So the next thing we have to do is we have to try to understand, like, how are we going to receive these arguments? So this is one of the other, building blocks to making functions. Notice how the assembly function, I'm sending it an integer, and then a float, and then another integer, and then another float. So I'm kind of mixing the arguments. Then at the very end, I'm sending in a pointer. If I look back up at the prototype here, which matches how I've used it, it's a long, a double, a long, a double, and a character pointer. So longs and doubles, they're called mixed arguments, and they don't actually count against each other when you're looking at the order of the registers to stuff them into. So for example, let me show you here. We have what did I just do? I clicked on the wrong computer. Okay, I'm on the wrong computer. Okay, let me close this real fast. So when you think about registers for incoming arguments, you basically start to think about this. RDI and RSI, those registers represent the first and the second integer arguments. If we look back to the book real fast, we can see in that same section, RDI is the first argument, and then RSI is the second argument, and then RDX is the third, and then the fourth. We can do up to 6 arguments with R9, and then after that, we have to start pushing arguments to the stack. I'm not going to go that far in this video. I've actually done that already in a previous video. But basically, for now, we can just use 6 registers to push arguments. But if you think about it, these registers, these are not floating point registers. These are general purpose registers. They're meant for integers and pointers. The reason they're used for pointers also is because a pointer is just an integer. A pointer is just a 64-bit integer, unsigned, which represents a memory location. So we can use these registers only for integers and pointers, but we can't use them for floats. So that means the first integer argument is going to be RDI, and the second integer argument is going to be RSI. But if there was a float argument in between, then RSI would still be the second integer argument. The floats don't count against the integers and vice versa. So, for example, if we're talking about float registers, the first one available is XMM0, and then we have XMM1, and then we have XMM2, and it goes all the way up to, I think, XMM15, so we have 16 floating point registers. So we could pass in 16 floating point arguments just using these registers if we wanted to. And then if we wanted to do even more than that, we'd probably have to get, funky with the stack or something, or maybe hopefully you just have an array somewhere and you're just going to pass in a pointer. But the way you have to think of these arguments is that even though they might be mixed in the prototype of the function that you're calling from a higher level language, you shouldn't think of them as being mixed when you're actually loading up registers. So again, if we just kind of like go back here to this prototype, notice how that A variable, we're going to say that the A is RDI because A is a long, it's an integer. But then right after that, there's a double B. We would not skip RSI or assign B to RSI. B would just be the first float argument. And then when we go back to long C is actually the second integer argument because that double doesn't count against the integer. So it's going to be C is going to be RSI. And then for double D, same thing. We're not going to skip XMM1 just because there was an integer. We're going to go straight to saying that XMM1 is the second float argument, so it's the D. Then for the last argument that we have, I'm just going to erase this stuff down here. It was going to be E, and remember, pointers are integers. They're just unsigned 64-bit integers. We have to go on to the next one, which I think I recall is like RDX. Let me just double check. I don't want to say this wrong. RDX, yeah, the third argument. So I'm going to do RDX. And now that we've kind of like mapped this out, we know now what registers we should be looking for. When the function comes in order to receive our data, we should look at those registers for those variables. Another thing to keep in mind, by the way, is that usually when we return something in assembly, we will move a value into RAX, right? Like some value, if you've been following my assembly videos so far. But that only counts if you want to return an integer or a pointer. If you instead wanted to return a floating point number, then you would have to use XMM0. And you're not allowed to hard code a floating point number in assembly like this, or at least in YASM. So we'll just pretend that there's like a float somewhere, and I'll just load it from memory, and I'll say like the float, something like that. So notice how we're using a different instruction. We're not using the regular move instruction that works with integers. We're instead using the floating point version. We're saying, let's move a single piece of data and let's move a double precision floating point number into XMM0. And then we'll just grab from memory whatever that variable has, we'll just take that floating point number and stick it into XMM0. So if you want to return an integer or a float, you use RAX. If you want to if you want to return an integer or a pointer, you use RAX. If you want to return a float, you use XMM0. You shouldn't do that at the same time. If you have like two assembly functions calling each other, you might be tempted to do that, and I guess nobody would really stop you, but your program would not be, you know, very standard, and it wouldn't work very well with other people's code or library code or higher level language code. So only one or the other, and it just has to match your prototype. So notice how here inside of my CPP function, notice how it's going to return a double, right? So when the assembly module is done calling on this function, it should expect XMM0 to be loaded up with that double precision floating point number. Okay, so that's the basic idea. So now let's, maybe let me pin this. Let's kind of fill this out a little bit more. So the first thing that we should do is we should save our integer or pointer arguments. So I'm going to leave the respect ABI thing there. And notice how I'm just looking at RDI and RSI and RDX. And, well, I guess, you know, we have it in a comment up here, A, C, and E, but I'll just make another comment here. I'll say like A and AC and E, and maybe we'll specify the data types for fun. So it's going to be long A, and then long C, and then a character pointer C. Even if this was a float pointer, it would still be an integer because all pointers are integers, no matter what they're pointing to. So just keep that in mind. Anyway, so we're going to save R12, R13, and 14 with the incoming arguments. And the reason we want to save those right away is because RDI, RSI, and RDX, those are not callee saved, which means the moment we call on another function, they'll possibly be destroyed because we don't really know what's going on in other functions that we might call. So it's a good idea to just kind of save right away, either to a global or the stack, or in this case, just registers, being faster. Okay, so we have that. Now we have to save our float arguments. And if you recall, B and D were XMM0 and XMM1. So I'm just going to save both of those. And if you're wondering what this float B and float D are, that's just, you know, up here. I just have a global variable. So I can save them to memory easily and not worry about the stack. This is not a stacked video so much. But yeah. Okay, so I'm just saving all of the incoming arguments. That's all I've done so far. And let's see, it should probably still compile. Let me see if this works. I'm gonna go make run. Okay, so nothing happens, but it at least worked. So I'm gonna, same as other windows for that, so that we don't have to look at it anymore. And now that we're done saving our float arguments, let's print a welcome message. So I'm gonna do, you know, welcome, and I'm gonna use a special function that I've made in previous videos called print null-terminated string, which means I should probably copy paste that into this program now. So what is print null-terminated string? It's just another convenience function that I wrote. I'm not going to explain it too much because it's in other videos, and I'm already here trying to explain functions to you in general. So long story short, it takes in a C string and a file handle, you know, to like where you want to write, like if you want to write to a file, or you want to write to standard output or standard error, and it just takes those arguments and then it sort of says, all right, how long is the string? And it uses another function called string length to figure out how long the string is, and then it just uses a system call to actually print the string. And again, system calls are covered in other videos. This one looks really convoluted because it's like, you know, customized for this function, but just trust me on this. This prints a string. Next function I got to paste in real fast, again explained in other videos, is the string length function. So all this does is it just takes a pointer to a string and it sort of scans the string, counting how large the string is. And as soon as it sees a 0, like a null terminator, then it just says, all right, that's the end of the string, and it'll just return the length to the caller. So that's all you need to know about this. Covered in other videos. Then I'm going to make a convenience function here called CRLF, and all that's going to do is just print the new line that we talked about earlier. So just a bunch of convenience functions on top of the real part of the program. So now that we have the convenience functions in there, we should be able to see the welcome message. Let me just double check that. Yeah, now inside assembly entry point. Oh, what did I do wrong? Now inside, I keep forgetting to change the strings on this. Now inside, where's that? Now inside my assembly function. Okay, let me change that in my solution too. You know, I'm just kind of like writing these things and I'm having fun and I keep changing my mind about what they should be named, and then I get some inconsistencies. Okay. All right, so then we printed the welcome message, and now let's print the integer arguments. But first, let's print a little introduction to the integers. Let's just say, hey, we're about to print the integers. So that's just this other string, a message saying we're about to print the integers. Nothing really that complicated so far. It says now we're printing all the integer arguments. So now we can actually print the integer arguments. So we have two integer arguments. Right now they're stored in R12 and R13, if you recall. Let's see. Yeah, we had like A and C. Those were integers. I'm not going to talk about E right now because that was a pointer, but right now we're just saying A and C. So that was R12 and R13. So I'm just going to paste some code here to actually print those. And talked about this library in other videos, but basically I'm moving R12, which is the first integer that I want to print, into RDI, which is the first integer argument that functions typically receive. And once that's loaded up, I'm just going to call on my special function to just print the integer. And again, you could use printf from the C libraries if you actually wanted to print it and not just experiment and stuff like that. So I'm going to use R12 and R13, and I'm just going to print both of those integer arguments. And then after each one is printed, notice I'm calling the CRLF function, which is just the convenience function of just like doing a new line. So now we should see two numbers. Yeah, now printing all integer arguments. We got an 88 there, and then that other giant number there. Let's just double check that that's actually what we're supposed to be seeing. So I'm going to do this, and I'm going to say the driver called the assembly module with these numbers. It gave it an 88, and then for the next integer, it gave it the 287 giant number. So great, we're printing the integers. Now let's print the floats. So we should see like a 99 point something and a 32 point something next. Okay, so let's continue with printing. Oh, sorry, actually, let's print the C string, because that's a pointer that's still more closely related than the floats. So the first thing I'm going to do is I'm going to let's see, print the received C string. How about like announce that we will print the C string? Because that's what we're doing right here. Let me change my solution to match. And then we'll actually print the received C string next. So same stuff as before. First we call print null-terminated string to print out a little welcome message, or just like an intro message, like we are going to print the C string. And then we'll use that print function again, but we'll give it the C string, so it just prints the whole C string out. And this should prove to you that we are indeed receiving a pointer to some data owned by the C++ module. So if we run this real fast, it should just tell us two more things. It'll give us the announcement, now printing the received C string. And then on that same line, it says, hello, this is the C string owned by main. And if we just look back at the driver real fast, that's exactly what string is inside of that variable. So hello, this is a C string owned by main, and we gave it to the function by just kind of passing it in. And we know that character arrays are basically character pointers, or any array is just a pointer to the first item in the array. So my C string is really a pointer to that H character. So if we pass that in, then a pointer-based print function should be able to work, and that's what happened. Okay, so we've done that, and then the next thing we should do is let's print the floats. So first, let's announce that we're going to print the floats. Same thing we did before, we're just printing like an announcement message. If we run the program again, it's just like now printing the floats, but it doesn't actually do anything. So then the next step is let's grab the first float into XMM0, and then let's call a function to print it. So right here we have like that 99 number that we expected from before. By the way, so why am I doing it this way? Why am I not just keeping XMM0? Because you remember before we had XMM0 had the float that we received, and then we're using it again down here. But remember, XMM0 and all the other float registers, they're not designated as callee saved, which means the moment we call any other function, we should expect that that data has been destroyed. So I can't actually count on XMM0 surviving just this little simple function. Instead, I have to save it somewhere, to the stack, to memory, whatever. So that's why I put that into a global variable. So it's sitting in float_b right now. And then we saved it at the beginning to float underscore b. And if you just kind of look up to the data area, well, it was just float underscore b was just a little quad word, 8 bytes of memory that can hold our float. So we have like float allocations for b and d, the first and second float arguments. So we're saving it there, and then we're recalling it here. And remember, the first function argument is going to be xmm0, regardless of where that data originally came from. So if we look at the next one here, if we kind of like, let's see, copy paste this, and we want to grab like the d float, we're still going to load it into xmm0, because right now it's not about what we originally received as an argument. It's what this function expects as an argument. This function only takes one argument. It just wants a float so that it can print it, and that's it. So both times we're going to load it up into xmm0. And then we're going to print a new line. Okay, so let me just run the program one more time, and we should now see we've got 2 floats, and they should match what the driver tried to send in, right? So 99, that's the first one, and then 32 point something, that's the second one. So cool, we have received integers and pointers and floats. We've recalled them, and then we've printed them. Pretty slick, what do you think? Anyway, so we've done that, and the next thing that we should probably do is, well, at this point, well, we just maybe have to mess with return types. Even though I've told you about it, we'll mess with it a little bit. But let's call the C++ module. So what I'd like to do first is just sort of announce that we're going to call on the C++ module. Again, typical design pattern, let's just print a message saying what we're about to do. And if we run this now, it's going to say, assembly module will now call on the C++ module. So nothing really too complicated. So now we're going to call on that function. Let me paste the name of it here. Actually, I'm going to put this one right here. It's the myCpp function. So if we look back at the driver and look at the signature for myCpp function, whoops, it has this signature. And if you wanted to look up higher, you totally can just look into the name mangling section. So, whoops, the myCpp function. It returns a double. It takes in a long, a double, and a character pointer. Basically the same thing as the other one, except it returns a double. So what's going to happen is when it takes all of these in, it's just going to print all of them. And then I'm just going to have it return just kind of like some random double that I decided to type, because this is not an arithmetic video. Okay, so CPP function, and then now how do we interpret that? So if we, let's see, let me maybe just for help, this usually helps me when I'm trying to do this. I'm going to take the prototype and just sort of like paste it right where I'm about to call the function. So I'm going to do this just to remind myself of what I'm actually calling. Let me add that to my solution, by the way. Okay. So we're going to call myCpp function, which means it's expecting some registers to be loaded up with arguments. If we don't actually load up anything right now, it'll probably do some sort of nonsense. Let's actually see what happens right now. If we don't load up the appropriate registers, then C++ will still look at those registers expecting to see valid data. Let's see what happens. I don't know if it's going to be good or bad. This would probably be something called undefined behavior, meaning you did something wrong, and probably sometimes your program will work and sometimes it won't, and sometimes you won't understand what's going on. So I'm gonna do this right now, and it's saying, oh, it's seg faulted. Okay. Okay. Why did it seg fault? All right. Well, I guess maybe because I did something naughty. I don't know. If this seg faults by the end, we're going to be in trouble. I'll have to debug on camera. So we're going to enter into myCpp function, and then it says we got a variable a, which was a long. We didn't give it a 1. A 1 was just probably sitting in there before we even called that function. So like 1 is definitely not it. And then b was like some, I guess, very, very, very small floating point number, and then c was just like another seemingly random value. That kind of looks a little bit more like a pointer. I'm not really sure. It's probably not, but it's just some junk data coming from somewhere. And then d, which I think d was supposed to be a character pointer. It says not a number, so we just got like a really bad value for d. Now let me upgrade this real fast, because maybe we should be printing it as a memory location. So e is let me bring this down real fast. So E is supposed to be a character pointer. Let me instead of printing the C string as just like itself, let's first print the memory location .E, and I'll just say memory, and then we'll do a static cast. Oh, I wonder if this actually changed anything. I wonder. Let's static cast both of them just to see what happens. So I'm going to print E and C string here, and then it's going to be no, I don't think that's actually going to change anything. Because if I cast it as a character, that's definitely wrong. And if I don't cast it, then it's going to show up as its original data type. How do I get the memory location? Oh, I know what to do. I can static cast it maybe as an unsigned long. Okay, so a character pointer, we'll leave that for the C string. Unsigned long, just in case. And I think I should see the memory location first and then the actual C string later. If not, then whatever. Let's try one more time. Oh dear. Invalid static cast from a character pointer to a type long, unsigned integer. What have I done? How about unsigned long? See if that works. Character pointer to long int. I guess I forgot how to cast pointers to longs. I'll look that up and post another video in the future, but I guess for now we'll deal with this humiliation. And I'll just print E by itself. All right, so I'm just going to run it one more time. It should segfault again. Okay, so obviously something is wrong. Let's just fix the arguments. So before we make that call, we should load up some stuff, right? So I'm going to do maybe like a semicolon comment here, and then I'm going to do, what else do I have? I've got 3 move instructions. So the first argument's going to get 77118. The second argument's going to get 1111. And the third argument looks like it's going to get a pointer that I've defined inside of the assembly module. So if you look back up at the top, let's see, message string inside ASM, message string inside ASM. So basically I'm going to be sending a character pointer to this T right here, which is just this string. It says this string is owned by the assembly module, and it's a null-terminated string, which C definitely needs in order to print correctly. If we took that 0 off, we'd probably get a bunch of junk data. We might crash the program. I don't know. So anyway, basically we're just going to be saying, you know, here you go. Here's a pointer. Where the heck am I? Okay, here's a pointer to a C string. And so we're giving it 1, 2, 3 arguments. We're giving it the A and the C and the E. Now we just have to load it up with the other 2 floats. So I'm going to do this real fast. Remember, the first float argument is going to be XMM0, and the second one's going to be XMM1. And you can see that send B corresponds to the first float argument. That's why it's XMM0. And then the float send D corresponds to the second argument. That's why it's XMM1, and that's the D right here, and there's no other floats. And if we just kind of look back up real fast, the float send B and D, I just defined those arbitrarily to just these 2 random numbers. So we should see like a 219 and then a 9988776 sort of, you know, weird number. Then when we're done loading all those things, you know, all of these registers up, now the function should be able to receive something. I bet you the reason it crashed is because we had like a bad address for the string previously because we didn't load it. So let me go up here, and now it doesn't crash. So if you just kind of like look, we have hard-coded A and B. Sorry, not A and B, A and also C. So that's the 771 and then the bunch of ones. And then the string, which was RDX, which was the E. So this string is owned by the assembly module. Nice. We're now able to print a string that's owned by assembly in another module, in the C++ module. And then XMM0 and XMM1, those are the 2 floats. So if we look back up again, that's we should expect to see these 2 numbers right here. Whoops. Float send B and D, which is B and then D. So the printing kind of turned it into scientific notation. That's okay. You know, there's other stuff you can do in C++ to just not print in scientific notation, but for now I don't really care. It's basically the same value, so it's fine. I just want to show you how to transport data. This is not a C++ video. Anyway, if we go back down, to the end of that. So we called the function, but then this function, if you notice, it returns a double, right? Which means we should expect to see something loaded into the XMM0 register. So I'm going to move a single piece of data, and it's going to be a double precision floating point number. And I'm just going to store it into my float got return value global variable, which I defined up above. So let me scroll up real fast. So where's that? Float got return value. I initialized it with a 0 just because we're going to receive something in there. I could have used the BSS section if I wanted to. Probably would have been a little bit smarter and more performant, but I don't know. I personally don't like using the BSS section in YASM unless I want to allocate an array. If I'm just doing one variable here and there, then I'm just going to put it in the globals or the data section. So float got return value, I'm saving it in there, and then I want to grab it from XMM0. So that's where it comes from. When my CPP function returns, it's going to return the double to us inside of XMM0. So I'm just moving that into my data section, into the global variable. And then, now that we have finally returned from the C++ module, I'm just going to announce that we have indeed returned from the C++ module. Let's get that far real fast. So this string is owned, and then my CPP function exiting, and then now it says the assembly module received this return value from the C++ module. And then it says the driver has regained control, because we were supposed to print the float and do a line feed after that, and we didn't. So basically, assembly just printed this string. That was the last part we just added, and then it returned right away to the driver. So let's finish this up. So next thing we're going to do is we're going to move the float value back into XMM0. Remember, anytime you call a function, all your float registers could be destroyed. So it makes sense that we saved XMM0 and then we loaded it only several instructions later, because you don't know what's happening under the hood inside a print null-terminated string or any of the system calls that it uses. Your XMM0 is likely destroyed, but you don't know for sure, right? So if you count on it not being destroyed, you might be introducing undefined behavior to your program, so that's not good. Anyway, so we're just loading back up from that global into XMM0, and then we're calling that function again to just sort of print the float, and it wants the float as argument 0. So we're just sticking into XMM0, and then we're printing a new line. So then when we're done here, run it, and now it says the assembly module received this value from the C++ module, and notice how it's that special value that I hard-coded. 1, 1, 2, 2, 2, 2, 2, whatever. So that's this value right here. And again, if we had this CPP function returning along, then all we would have to do is look at the RAX register. And if we had, let's say for some reason that this assembly function, we wanted to get something from it, we could say, double temp equals that. Then all we'd have to do is make sure that we returned, we loaded XMM0 with our return value in the assembly module, because XMM0 is the return register for floats. Or if we wanted to do like a long, then just load RAX with something at the end of my assembly function, and that's how C would be able to get it. Remember, C is following, C and C++, they're following the ABI. So if you personally don't follow the ABI, you're just going to end up memorizing two different ways of doing things, and your way is not going to be compatible with all the other modules written in higher level languages. So it's kind of a waste of time, and your modules won't be compatible with other people's libraries and functions. It's just a huge waste of time. So just follow the ABI in the first place. I've literally known people who said, you know what, I don't want to learn the ABI. That's dumb. Then as they wrote a bunch of assembly, they just started thinking like, oh, this is too confusing because I keep forgetting what registers I was going to pass back and forth between my functions. And like a month goes by, I come back to an old program. I can't remember. I have to like look through all my code again. So then they started accidentally inventing their own little scheme. Like, oh, I know what to do. I'll put the first argument in this register and I'll put the second argument in this register. All they were doing is just reinventing the ABI from scratch and then wasting a bunch of time before they got to that point. And then later wasting more time when they realized they just needed to learn the ABI and forget about their way. So don't let that happen to you. You should probably just try to do it the right way the first time, right? A lot of things in coding and computer science in general are just time savers that feel like wastes of time at first. Okay, what else? Do we have anything that I wanted to show you? That was actually, I think, the entirety of that program. Let's run it one more time for posterity while I check to see if there's any other stuff that I was supposed to show you. So let's do this. Everything seems to be working. Let's see, I wanted to tell you about labels, return, call, the stack, the return address, Prologue and epilogue, pushing and popping, respecting the ABI. I wanted to show you that textbook. Function arguments, mixed arguments, int or pointer, return types and float return types. I guess I got through everything without forgetting something huge, which, hey, that's probably a first. Not that I recall at the moment, but it probably is. Anyway, so I guess that's it. I hope you feel like function experts now in YASM x86-64 assembly, also known as AMD 64 assembly in Ubuntu. Okay, thank you so much for watching this video. I hope you learned a little bit and had a little bit of fun. I'll see you in the next video. Hey everybody, thanks for watching this video again. From the bottom of my heart, I really appreciate it. I do hope you did learn something and have some fun. If you could do me a small little favor, could you please subscribe and follow this channel or these videos or whatever it is you do on the current social media website that you're looking at right now. It would really mean the world to me, and it'll help make more videos and grow this community. So we'll be able to do more videos, longer videos, better videos, or just I'll be able to keep making videos in general. So please do me a kindness and subscribe. You know, sometimes I'm sleeping in the middle of the night and I just wake up because I know somebody subscribed or followed. It just wakes me up and I get filled with joy. That's exactly what happens every single time. So you could do it as a nice favor to me, or you could troll me if you want to just wake me up in the middle of the night. Just subscribe, and then I'll just wake up. I promise that's what will happen. Also, if you look at the middle of the screen right now, you should see a QR code which you can scan in order to go to the website, which I think is also named somewhere at the bottom of this video, and it'll take you to my main website where you can just kind of like see all the videos I published and the services and tutorials and things that I offer and all that good stuff. And if you have a suggestion for clarifications or errata or just future videos that you want to see, please leave a comment. Or if you just want to say, hey, what's up? What's going on? You know, just send me a comment, whatever. I also wake up for those in the middle of the night. I wake up in a cold sweat and I'm like, it would really mean the world to me. I would really appreciate it. So again, thank you so much for watching this video, and enjoy the cool music as I fade into the darkness which is coming for us all.